Hello and welcome to today's not tutorial, but a theoretical explanation. This explanation is on PID controllers and on the values P, that's this one, I, and D. What do those actually mean? Right? We have the P, which stands for proportional. We have the I, which stands for integrational. Right? It doesn't really see here, but integrational. Then we have the D for derivative. There's integral sum, integration. We have also it's written here. So what do these actually mean? We will see in this video. Quick explanation. First of all, again, here is my controller that I have programmed, and it works somehow, right? So we have some slope here. We want with the black one, we want to get to the green line, which is the set point, which I can change here. So 6 liters, for example. Let's get there, and the black line will be when at the green line, and it's auto adjusting now a little bit, so it's somehow around it. Those values, if we fit them perfectly, it will be perfectly on the green line very fast and so on. But this is what I've covered in the last video in the tuning. This time we want to see what do those three values actually stand for. Therefore, I have this little switch here. If I deactivate this little switch, then my PLC output won't be active anymore. My controller can still act, right? My controller can still act. So the red one, this is the PLC output. The PLC output can still change, but the black line, there will be no inflow into the tank itself, into the left here. If I turn it on again, we can see there is flow into the tank again. So let's have a look at P, I, and D. Right now I set them all to 0, meaning the red line here, this is my PLC output, the red line definitely also will go to 0, right? That's the first thing. The second is I want to go to 5 liters. My set point is right here in the middle, right here in the middle. Next thing, my tank is 10 liters. Do you see it? 0 until 10. So 10 liters is the maximum, meaning 10 liters is 100%. If I want to go to 10 liters, meaning I want to go to 100%. If I want to go to 5 liters, I want to go to 50%. Last thing on this, I have a current level. My current fill level is 0% because it's empty. If it's half filled, it's 50%. If it's completely full, it's 100%, right? So the fill level is also in the same range as the set point. One more on this, we have a so-called error. The error is the following. I want to go to 5 liters right now. I have 0 liters, so the error is 5 liters. If I want to go to 7 liters, the error is 7 liters now, right? Or in other words, 70%. If I want to go to 10 liters, this is the maximum error we can have, 100%. Right? This is the biggest error we can have in our scenario. Meaning, the bigger the error, somehow the stronger my controller will react. So, let's have an error of 50%. I want to go to 5 liters, I have 0. 50%. If I now add a proportional gain, so the first is the P factor, the proportional gain. I have a proportional gain of 1. 1 means, in our case, multiplying the error that we have. The error is 50%, right? We have 0, we want to go to 50%. The error is 50%. So taking this error, multiplying it with the proportional gain, which is 1. So 50% times 1, that's 50%. And putting that on the output. So my PLC output, the red line here, will also be 50%. If I have now, let's say, a proportional factor of 0.5, we have in total here from the black line to the green line an error of 50% times 0.5. That's 25%. So my output will be on 25%. If I want to have the output now on, I have a 50% error, but I want 100% on the output side. I have to set the proportional gain to 2, and you see it's 100% now my PLC output. A good value in the beginning here is 1 to see what the outcome will be now for my real output. If I turn on the pump now, meaning my pump will react, I have now an error of 5, right? 5 liters or 50% with a proportional gain of 1, 50% on the output side. Now, if I turn the pump on, my fill level will increase, my error will decrease, right? Because we are closer to the 5 liters. Meaning my gain will be the same, but my error will be smaller. And the smaller my error, the less the pump will be on. So let's see how that looks like. I turn it on. And you see my fill level is rising. And proportionally, really, that's why it's called a proportional, right? A linear proportion here. My PLC output will react on that. So right now I have here approximately 40% in my tank. The error is 10%, meaning my pump will be on for 10%. If I increase the proportional gain now to 2, you will see it jumps to 20%. The tank will be filled a little bit more, right? And we will be stuck again at the same, at a similar value. We will be stuck again. If I increase my gain more and more, we are getting closer to the 5 liters, right? We're getting closer, but not really close. You see it? We still have this error here. We still have this error. This is the so-called steady error. If I make my proportional gain too high, what's going to happen? I will go above my fill level, my set point, and below, and above we will start oscillating. So we should avoid oscillations. We should have a smaller gain. Maybe in this case 8 would be good. But this is tuning again, not looking at this in this video. Okay, 8 is too much already. Let's stick with 1. So that's the P. It's a proportional gain. The bigger our error, the bigger our output. Now, the Siemens PLC, the PID compact, works in such a way that we always need a proportional gain. If I do not have a proportional gain, the others will not affect my output. So my output, whatever is in the integrational and in the derivative, multiplies with the proportional gain, right? So I always need a proportional gain. That's why it's good to have that at 1 or so. But let's see. See, I changed those and nothing happened here. Next thing, the reset time, the integration part, the I part, right? The integration part given in seconds is the following. If I have an error of 100%, it will take, if I put in 10 seconds here, it will take that amount of time to turn on my controller to 100%. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It took 10 seconds to fill this integral sum to 100%. 100% means that the controller would be on 100%. So let's see. I give it a proportional gain and I reset everything. And now we should be able to, yeah, it's just 0.1. I need, of course, 1. I will start with an error of 5, right? I'm already at 5 liters. There we go. You see, I want to go to 5 liters. I right now have 0 liters in the tank. So it will take, if I have a reset, this is an error of 50%, right? 50%, meaning it will take now, you see, 20 seconds to actually get to the 100%. Because I only have 50% of the error, it will take 20 seconds, but I already have 50% from my integral, from my proportional part, so it only takes half the time here, so 10 seconds. So what does that really mean for the PLC output? Let's see. So I turn it on. Maybe let's check it again without the integrational time. So this is what it looks like. The last part here, starting here, this is what it looks like without integrational time. We just have the proportional. The closer we get to the error, the less our output is on here. The closer we get to the error, the less our output is on. If I add now a reset time and integrational time, maybe 10 seconds. Let's make this empty again. Our integrational time will add up to this. This is additive, right? It's additive. So we will get actually closer. You see it? We will get closer to the error. The problem right now is we will have overshoots because it's too big. It's too fast. I should make that slower. And as soon as we are above, you see this value is actually going down again. So we are actually also going down there. So this is actually already better, right? We will at some point in time get to the green value, but I don't want this much of an overshoot. So I could maybe have 20 seconds, and this should actually be a nicer design because it doesn't react that fast anymore, right? So let's see, this looks decent. This looks decent. We still have overshoots, I assume, a little bit. Not too much. Oh, this is already a nice controller design. That's the integrational. It sums up at a certain time, and it will be on a specific level then later on. For closing this gap, right? We had this gap here, the steady error. We get rid of the steady error. The last one, the derivative. The derivative time, let's see, let's turn this off again. The derivative time is acting on a change of error. If I put in something now, let's say I want 5 seconds. You see, nothing has changed. Nothing has changed. It will only change if we change the error here. So if I put this to 0, nothing happens. But if I put it to 5 now, you will see, oh, my output is on for 1, 2, 3, 4, 5 seconds. Right? So my output will be increased on a change of an error. Right? And for as long as we set the time here, if I just set this for 1 second, and I go to 0 and I go to 5 again, 1 and we are directly there again, right? It adds on top of an error change. So if I have here, for example, 20 seconds, you will see this will now take a long time. And you can see it's always this nice curve. So it starts very strong and it gets weaker over time, damping out the errors, right? It's dampening. The problem is, if I now have some spikes on my fill level, if I have errors in my system, this will actually increase this error, right? It will multiply with the error, so it can be very aggressive. That's why usually we only take a PI controller. A PI controller is most of the times the design we want to go for. Right. All right. What does this one actually look like on the real controller? Let's see. You see, we start very strong here. We start very strong. This is the derivative, right? And you see, we're kind of, yeah, this is now the proportional again. The derivative doesn't really do much right now because the error doesn't change that much. The error changes a little bit. We can see those oscillations. This is actually now the derivative part. But if I change my error, meaning I want to go to 10 and to 5 back again, you can see it's acting very, very strong, almost binary on this level already. Derivative. But in the end, the best in most cases is a PI controller. And you see those values here are actually pretty decent for my case in this system. Could be improved a little bit because in the beginning here it could be stronger. So maybe even a proportional of 2 would be nice. We will have a bigger slope. Do you see the slope? This one here? It's way bigger. But you see we have overshoots now. But yeah, this little overshoot is actually not that bad. This is still good, depending on your system design, depending on what you exactly need. So that was a short explanation on P, proportional, I, integrational, D, derivative. Not the last thing, thank you for watching. I hope this helped a little bit. If you still have questions, put a comment in the box below, in the comments below, leave a like, subscribe, and thank you for watching. I will see you in the next video. Bye bye.